Hello everyone, my name is Ayush Gupta and today I am presenting our work on visibility aware switching between radar and LiDAR for robust SLAM in degraded environments. This project was a collaboration between myself, Arjun Ramchandran and Shivam Mudeshi as part of our mobile robotics coursework. The core motivation behind our work is to develop a perception system that can adapt in real time to varying environmental visibility conditions, something that's crucial for autonomous vehicles and mobile robots. So let's dive right in. The motivation behind our project, as you can see, that autonomous vehicles and mobile robots rely heavily on optical sensors like LiDAR and cameras for tasks like SLAM and object detection. However, these sensors degrade significantly under conditions such as fog, smoke, rain, or even dust. This creates major reliability issues in scenarios such as search and rescue, post disaster response, or industrial operations, where conditions can't be controlled. While some studies have focused on multi-sensor fusion, combining LiDAR and radar or camera with radar, these approaches require all sensors to be active at all the time. That results in high energy and compute costs, which is impractical for battery powered or embedded systems. Radar, on the other hand, is robust under poor visibility but has limited spatial resolution. So the question is, what if we could use the strengths of both? That's where our work comes in. Building a visibility aware system that dynamically switches between LiDAR and radar depending on environmental visibility. This adaptive approach helps maintain the perception reliability while also saving energy. So let's now frame our problem statement. As you might have already guessed, our problem is twofold. First, how do we maintain SLAM accuracy when optical sensors fail? And second, how do we reduce energy consumed by avoiding unnecessary sensor usage? Our proposed solution is a visibility aware switching framework, which instead of running all the sensors at once, the system dynamically selects either LiDAR or radar based on real time visibility assessments.
Okay, so now I'm going to explain about the data collection methodology that we've done. So starting off, we've used Carla simulator for our data collection. Specifically, we chose the town 2 environment to create the consistent trajectories across different visibility conditions. We have collected LiDAR and radar point clouds both in clear weather and under simulated dense fog environments. We mainly use clear weather for LiDAR data collection to present as a ground truth for our neural network training process. And this allowed us to generate training pairs of both high quality LiDAR scans and correspondingly sparser radar scans. High quality LiDAR and sparser radar scans. So to maintain consistency, we downsampled the radar point clouds to 256 points and LiDAR to 2048 points. This ensured that our deep learning model could train on uniform input dimensions while retaining the essence of each sensor's characteristics. So moving on. Here we have our system architecture, and it's just a high level view of how our architecture works. So we'll start with collecting radar and LiDAR scans in clear environment, and we store the scans and we train our point net neural network, which is a 1D convolution neural net, which will train to predict basically radar, how to project radar scans onto our similar to our LiDAR scans. We do the testing after the training in a fog environment while collecting LiDAR and radar scans, and yeah, we perform a switching algorithm to between radar and LiDAR, and finally the radar to LiDAR model predicts the LiDAR point clouds that are translated from radar, and the final step is performing SLAM on these LiDAR predicted point clouds.
Okay, now let's look at the algorithm to understand the system at the deeper level. We have two algorithms in front of us which illustrate the complete point net pipeline, starting with the training on the left and ending with the prediction and visualization on the right. So in the algorithm 1, which we have on the left, we first initialize the Kala simulator and attach the sensors to a vehicle. This includes a LiDAR and 3 radars. Then, in a continuous loop, we collect the synchronized sensor data and vehicle poses and save them only when a valid data is present. Once we have enough frames gathered, we voxelize the point clouds into a 3D grid format and use those to train a 3D CNN model that learns to predict the LiDAR data from the radar input using binary cross entropy loss and Adam optimization. On the right, we have the algorithm 2 that shows how this trained model is used in practice. For each incoming radar frame, we voxelize it, run inference through the model to predict the corresponding LiDAR grid, threshold the output, and convert it back into a 3D point cloud. These predicted points are then saved and visualized along the actual map and the trajectory with different colors to clearly compare the prediction quality. To train the network, we use chamfer loss distance as our loss function. It penalizes both missing points and redundant points by measuring bidirectional distance between the predicted and the ground truth point clouds. Chamfer loss is a common distance metric used to compare two sets of points, often used in 3D vision, point clouds, and even deep learning applications like shape reconstruction. Imagine you have 2 point clouds. One is the predicted output from your model, and the other is the ground truth. Chamfer loss ensures that every point in the predicted set is close to some point in the ground truth and vice versa. Mathematically, it works in two parts. For each predicted point, it finds the closest ground truth point and sum those squared distances. Then it does the same in reverse from each ground truth point to the predicted set. This bidirectional matching makes chamfer loss more robust to differences in density of ordering of points. It's popular in tasks like shape completion, LiDAR-based SLAM, and neural point cloud models because it's simple and differentiable. To enhance the robustness, we also inject Gaussian noise into the radar inputs during the training. This ensures that our model generalizes well to the real-world radar noise and variability.
So as you can see, this slide shows the output of our adaptive system. The blue points are LiDAR scans from fog conditions, and the purple points represent the radar inputs that were translated into LiDAR-like outputs. As you can see, even in dense fog conditions when LiDAR performance degrades, our system switches to radar and still maintains structural consistency. This confirms that the switching logic and point cloud translation preserve map geometry, which can enable us to perform continuous LAM operations. For future, we can, instead of a hard switch logic, explore soft fusion strategies, which use learned context from weather, environment, or task priority. This can make our logic more adaptive to weather conditions and environment conditions as well. These are some of the references that helped guide our project and formulate our constraints.